Good morning, grade 9. Our lesson today is we're going back to Algebra 2. Our lesson is Chapter 5, Lesson 1, Variation Functions. Variation Functions. You have studied many types of linear functions. One special type of linear function is called direct variation. A direct variation is a relationship between two variables, x and y, that can be written in the form y equals kx, y equals kx, where k is not equal to 0. In this relationship, k is the constant of variation. For the equation y equals kx, y varies directly as x. Y varies directly as x. Again, let me say it again. As we studied many types of linear functions, one special type of linear function is called direct variation. Direct variation is a relationship between two variables. And as we know that x and y are variables, so a direct variation is a relationship between two variables x and y that can be written in the form y equal kx, where k is not equal to 0. In this relationship, k is the constant of variation. For the equation y equal kx, y varies directly as x. Y varies directly as x. What does this mean? It means that if k is positive in a direct variation, the value of y increases as the value of x increases. The value of y increases as the value of x increases. Okay, let's take the first example here, writing and graphing, given that y varies directly as x and y equals 14 when x is equal to 3.5. Write and graph the direct variation function. Write and graph the direct variation function. The direct variation function, I can write it as y equals k of x. Y is equal to k of x. Let me, yes, this is the form that I'm going to use it. I have the value of y here, and I have the value of x here. So I'm going to substitute the value of y by 14 and the value of x by 3.5. Okay, then I'm going to get the value of k. Then I'm going to write back the direct variation function. Y is equal to 4x. Y is equal to 4x. Let's watch this video together.
Variation functions, where we can actually see how one variable affects the other variable in a very systematic way, a very predictable way. Let's start off with direct variation. So direct variation is when we have a function of the form y equals a constant times x, where the constant is non-zero, is a non-zero number. When we see this, then we can say that these x's and y's actually are together in a direct variation. So this is direct variation. Let's take a look at an example where we can see this in action. So given that y varies directly as x, and y equals 10 when x equals 2.5, our mission is to write and graph the direct variation function. So the moment it says that y varies directly as x, that tells us that the function is going to look like this. For some constant k, k is an unknown number. It's not a variable, it's an unknown number. Our mission is to find k. How can we find k? Well, if we know one x and one y that correspond to each other, we can always find k. And happily, in this example, we're told that y equals 10 when x equals 2.5. Well, that's enough to find k, because check it out. If I put in 2.5 for x and 10 for y, I can solve this for k. And that k is going to be the k that's going to make this direct variation function. So let's start by finding k. Now, it's a very specific k for this example. You might even say it's a special k. So what we have here is 10 equals k times 2.5. So if I divide both sides by 2.5 in order to get k by itself, what we see is k equals 4. So if k equals 4, that means that my direct variation is y equals, the constant now we see is 4x. So we're looking at y equals 4x. Okay, so if we want to consider what that looks like graphically, we see it's a straight line. And we can plot some points if you want. For example, when x equals 0, we see that y is 0. So the origin is on there. When x equals 1, y is 4. So when x equals 1, y is 4. We know it's a straight line, so I know that's enough to actually produce this beautiful line. And so this is the graph of the direct variation, and you can see it's linear, and that's always true. Direct variation always is a linear function. And we can actually check this if you want to. My graph doesn't go up that high, but if we now plug in 2.5, so here's 1, 2, 3, so 2.5 is right here. If we run up to it, are we going to be at 10? Kind of hard to read off my graph, but on that graph, you can see it perfectly. In fact, let's focus on that. And you can see it goes right up to 10. So great. You can see this actually corresponds to the initial data point that we were given at the beginning, and we can actually now have a direct variation specifically.
Okay, girls, we have another example now. Next page, page 314. Solving direct variation problems. The circumference of a circle C varies directly as the radius r. C varies directly as r. So the relationship between C and r is C equals to K r. C is equal to K r. And C is equal to 7 pi feet when r is equal to 3.5 feet. Find r when C is equal to 4.5. Again, there is a direct variation between C and r. So the first relationship here, I'm going to focus on it now. C is equal to K r. Okay, girls? So when C was 7 pi, r was 3.5. They want to find r when C is 4.5 pi. So first I will get the value of K. Okay? So C is equal to KR. What is the value of C when R was 3.5? C is 7 pi when R is 3.5. So I'm going to substitute the value of C, which is 7 pi, with R, which is 3.5, to get the value of K. So 2 pi is equal to 7 pi is equal to 3.5 K. So to cancel 3.5 or to get rid of 3.5, divide both sides by 3.5. So then when I divide 7 by 3.5, I will get 2. So 2 pi is equal to K. Now I'm going to solve for K. Write the variation function again. C is equal to KR, but with the new givens. Find R when C is 4.5 pi. So when I'm going to write again here, C is equal to KR, I'm going to substitute the value of K with 2 pi. Why? Because I have here the value of K is 2 pi. So I'm going to put it here. So C is equal to 2 pi multiplied by R. So C is 4.5 because they told me 4.5 multiplied by K, which is 2 pi multiplied by R. So R is 2.25. Okay, girls? Okay, girls, let's solve another example. Example number 2, the parameter P of a regular dodecane varies directly as the side length S. P varies directly as the side length S, and P is equal to 18 when S is equal to 1.5. Find S when P is equal to 75. Let me write the answer here. First of all, the parameter P of a regular dodecane varies directly as the side length S. So since it varies directly, so it has the relationship which is P equal to KS. Okay, first I want to get the value of K. So when P is 12, when S is 1.5, so P is 18 equals to K, and S here is 1.5. So the parameter P of a regular dodecane varies directly as the side length S, and P is 18 inch when S is 1.5 inch. So when P is 18, S is 1.5. So I want to get the value of K. How I will get the value of K? I will write the variation function P is equal to KS because P and S varies directly. 18 is equal to K multiplied by 1.5. So 18 divided by 1.5. So K is equal to 18 divided by 1.5, which is equal to 12. I want to move it. Yes, I can move it here. Okay, is equal to 12. Next, second step. Okay. I want to find S when P is 75. So again, I'm going to write the variation function. P is equal to KS. P is 75 equals to K. What is the value of K? 12 multiplied by S that it is required. It is required to get the value of S. So 75 divided by 12. So S is equal to 75 divided by 12, which is equal to 6.25 inch. And don't forget, please, to write the units. The units are so important. Okay, girls, let's watch another video.
That involves direct variation can be done in a variety of different ways. I want to show you 2 ways of looking at things. You should find the one that you like the best and embrace it as your own. But they're both correct, and you can use either one. So here's the question. The value of y, we're told, varies directly with x. And y equals 6 when x equals 30. Our question is to find y when x equals 45. But one way to do it is just to actually try to find the formula for this direct variation. Well, how could I do that? Well, I know the formula will equal y equals k x, because I'm told that y varies directly with x. So there we have it. We also know that it's going to satisfy the following. When x equals 30, y has to be 6. That means if I plug in 30 for x and 6 for y, this equation has to hold. That will allow me to figure out the k. So in particular, I'd have 6 equals k times 30. And if I divide both sides by 30 to undo the multiplication of 30, I would see that k equals 1/5. And so I'd see that y equals 1/5, that's the k, times x. So that's the actual direct variation. You might think that's the end of the question and that we're done, but no, because remember, the question is to find y when x equals 45. So what do I have to do now? I've got to take this expression and let x equal 45 and find y. So if I plug in 45 for x, I see that y equals 1/5 times 45. And so that's the same thing as 45 divided by 5, which is 9. And so the answer is 9, right? When x is 45, y is going to be 9, given that they vary directly and they satisfy these two things. So that's one way, and if you like that way, that's great. But there's a different way, because in fact, when you have a
So for today, girls, we learned direct variation. Tomorrow, we're going to learn joint variation and inverse variation. Thank you, girls, for listening. See you tomorrow. Bye.